Hello everyone, my name is Subrata Samanta and I am from IIT Kanpur. So I am your tutor for the physics subject. So in the previous class we have learned about some electric flux, okay, how to calculate the electric flux and uh, so we define the electric flux basically for a small area element, okay, and if we calculate the flux over a surface S, so we first split this surface into a small area element, okay, and then we get a total flux. So so today I will do some examples, okay, and then it is become more clear. So example 1. So let's calculate the flux. So let's calculate the flux through a sphere of radius r, which encloses a point charge q as its center, which encloses a point charge q, okay, as its center. Okay. So how to calculate? So let's first split the sphere into a small elements, okay, and we consider the element, the area of this element is delta S, because now this one is a surface, okay, and so this one is a closed surface, so the area vector is pointing radially outwards, right. So the first step is that divided the sphere into small area element, divide the sphere into small area elements, and the second one is calculate the flux through an area element delta S, right. So a small area element, let us say consider delta S, and the second step is that the flux, we know that the flux through area element delta S is, so define the flux in this way, so delta phi E dot delta S. So the main reason behind this, that why we consider a small area element delta S when we define the flux. So basically we consider the electric field is constant over the surface, so that is why we consider a small area element, okay. So otherwise this concept is not valid, okay. So the electric field constant. So now we know the electric field for a point charge. If we place a point charge at its center, the radius is r, okay. So what is the electric field at that point? Let us consider the P point on the surface of the sphere. So the electric field at that point, q over 4 pi epsilon naught r square, right, and what is the directions? R cap, right. If the radius is r and the direction is r cap, n cap, so the direction is small r cap, and the delta S vector, okay, so the area vector is radially outwards, so n cap ds, right. So in this case n cap is r cap, right, for a closed surface, closed spherical surface, okay. So n cap basically r cap. So then then this one becomes, gives 1, okay. So the delta phi becomes q over 4 pi epsilon naught r square times delta S. So now if we consider the limit delta S tends to 0, so delta phi, so the total flux phi, total flux phi limit delta H tends to 0 sum over all the area elements q over 4 pi epsilon naught r square delta S. Okay, the sum over delta S. Okay, sum over all delta S, all delta S. Okay. So now this sum becomes an integral. So q over 4 pi epsilon naught r square and ds. Okay. Since that r square is a constant, the radius. Okay. So integrate over the small area element ds, and this one gives. So what is the area of a sphere? So q over 4 pi epsilon naught r square times 4 pi r square, the area of a sphere of radius r. So the left one is that q over epsilon naught. Right. So this is the flux passing through a sphere. Okay. If we put a charge on the of its center, okay, of the sphere, it does not depends on the. So the main important thing is that it does not depend on the radius of a sphere, right? So if we consider any closed surface, okay, so it need not be a sphere, okay, in any shape. If we put a charge inside it, okay, the flux through the surface is q over epsilon naught. So that is a strong statement, okay, and that is the Gauss law. Say that. Okay, so we will discuss this. So this one is a general result. Okay. So simple illustrations of, so this one is a simple illustration of a general result. General result of electrostatic called Gauss law. So why I am saying here this is general result of electrostatics? Because if we consider a surface that is arbitrary shape, okay, closed surface, need not be a sphere, and if we put a charge q anywhere in that, okay, then the flux through the surface is q over epsilon naught. Okay. So if we put another charge q1, let us say q2, q3, okay, and if we consider a surface that closes all the charges, encloses all the charges, then the total flux phi is becomes q1, q2, q3 by epsilon naught. The total charge q1, q2 plus q3 by epsilon naught. Okay. So we put a charge here q, right, and consider the surface here. There is no charge encloses within the surface, right. Then the flux through the surface, okay, flux is become vanishes because there is no charge encloses by the surface. So that is the general results of electrostatics, okay, and we will discuss more when we learn about the Gauss law. Okay. So so let's start with the Gauss law. So Gauss law basically says the electric flux through a closed surface S is q over epsilon naught, where q is the total charge enclosed by the surface S. So where q is the total charge enclosed by the surface S, and epsilon naught, you know that the permittivity of the free space, right. So epsilon naught is a constant permittivity of the free space. And the total flux, electric flux, so total electric flux through a closed surface is 0 if no charge is enclosed by the surface. Okay, so that we discuss here, right. So if we consider a closed surface here, so this one is a closed surface, remember it is not a open surface, it is closed surface, then the phi is 0. If we consider an open surface like this one, so the electric field lines, okay, so originated from some charge distributions, okay, that is the E, and we place a surface ds, this is not a closed, okay, then we find a non-zero phi, the flux through this surface is not 0, okay. But if we consider a closed surface that does not enclose any charge, okay, then the flux through this closed surface is always 0. So this is open surface. Okay, so that's all about Gauss law, and so now we do some examples and discuss the applications of the Gauss law. Okay, so let's do another examples. So let's consider a closed cylindrical surface. So let's consider a closed cylindrical surface, closed, yeah, so closed cylindrical surface, I will draw the surface. So this is a closed surface and this one is a surface 1, this one is a surface 2 we denoted, and this one is a surface 3. Okay. So yeah, so basically the surface 1 and 2 are the circular cross sections, okay, I mean that this one, okay, and the surface 3 is the curved cylindrical part, okay, and we calculate the flux through each surface, okay. So and if you consider the electric field are uniform, okay, so the electric flux passing through the surface 3 is 0, right. It is easy to understand that if you consider the electric flux, so the electric flux passing through the surface 3, so it is phi 3. So the area vector in that surface is perpendicular to the electric field, right, n cap. So therefore the cos 90 becomes 0, okay, gives 0, E dot ds vector, this one is 0. So the electric flux passing through the surface 1, this, right, so denoted the phi 1, that means the electric flux passing through the surface 1, so this one becomes minus E S1, right. If we consider the area of the surface is S1, okay, and the area of the surface 2 is S2, so it is minus E times S1. Why there is a minus sign? So in this case the area vector in these directions, okay, but the electric field vector in this direction, right. So if we consider dot product, okay, so then there is a minus sign, okay, because cos 180 degree gives a minus 1, and similarly for phi 2 is plus sign Es2, right. So again we consider a total flux phi 1, phi 2 plus phi 3, all the surface, we can consider a closed surface, and that gives a 0, right. It is not 0 because so basically the thing is that E S1 minus S2 minus S1. Now we consider a, so now consider a cylinder, that means that S1 and becomes an S2, so S1 S2 it S, so this gives a 0, and that is expected by the Gauss law, because in the cylinder there is a no charge, okay, and this one is a closed surface, so which one is expected from Gauss law. So in this two example we consider the simple cases, okay, and verified the Gauss law, okay, and the Gauss law is a more general statement, okay. So we pointed out things in a following manner. So Gauss law is true for any closed surface true for any closed surface. It does not depends on the shape and size, okay. So you can consider any surface, closed surface, and the flux through the surface is q over epsilon naught if there is a charge q enclosed by the surface, okay, no matter on shape or size, okay, no matter on shape or size. The flux phi is basically the sum over qi or epsilon naught, okay. So the surface encloses by the total charge, okay, q, basically sum over qi. If we say there is a too many charges q1, q2, q3, okay, it basically the sum over all the charges, okay, qi, the sum over all the charges. So in the next class we will discuss the applications of some applications of Gauss law and how to use symmetry calculate the electric fields, okay, either way to calculate the electric fields, okay. So okay, we will see in the next class. Thank you.